Welcome to Lesson 2 of Module 1. Today, we will cover how neural networks learn. We will begin with a review of the single-layer network, also called the perceptron. We will build upon this for the multilayer perceptron. Then, we'll briefly review optimization. Finally, we'll conclude with training a neural network. Let's recall the single-layer network, also called the perceptron. First, consider linear regression from a slightly different perspective. Concentrate on the information flow, or information processing, from input, on the bottom side of the line in the neuron, to output. On the upper side of the line in the neuron, linear regression assumes a linear relationship between input variables, such as x1 and x2, and the single output variable, y, as shown by the linear regression equation on the slide. With a diagram, you can visualize what happens. Given some inputs, two are shown here for simplicity, x1 and x2, along with the bias, 1, linear regression takes the inputs, weights them accordingly by weights w0, w1, and w2, sums the weighted inputs, and examines the weighted sum. Linear regression then passes that sum along to the output, O. If this output doesn't match the target value, y, then, based on how large the error output is, the weights w0, w1, and w2 are adjusted to make the linear regression produce outputs that are closer to the target value, which reduces the error. This is done several times until better w0, w1, and w2 are learned from the training data. This provides you with a more reliable model that you can trust, later for prediction. You can do the same thing with logistic regression by using the sigmoid function instead of a linear function. The neuron represents a logistic regression model that is suitable for binary classification tasks. So far, we have only discussed networks with one layer. Typically, networks will have many layers. How can you go beyond one unit, one neuron? And why would you do so? As mentioned, a limitation of the artificial neuron is that it captures mostly linear interactions in the data. Can you use a similar approach to capture nonlinear interactions in the data? For example, consider the traditional XOR problem. Give 4 XOR data points, blue circles and orange triangles, separate the blue inputs from the orange inputs by using the concept of an artificial neuron. A XOR problem involves using a neural network to predict the outputs of XOR logic gates given 2 binary inputs. An XOR function should return a true value if the 2 inputs are not equal, and a false value if they are equal. The artificial neuron that is shown on the left side of the slide is only capable of separating data with a single line. Unfortunately, the XOR data points cannot be separated linearly, that is, any line that you would consider would not completely separate the blue circles from the orange triangles. Therefore, adding a neuron allows you to capture nonlinear interactions in the data. There are several components of a multilayer perceptron. These neural networks consist of input, hidden, and output layers. Each layer is connected to the next layer. An activation function is applied on each hidden layer and output layer. Starting with the input layer, this is the first layer in a neural network, and it receives the input data. The number of neurons in the input layer is determined by the number of features in the input data. Hidden layers come after the input layer, but before the output layer. They are called hidden because their internal workings are not directly visible from the outside. The hidden layers are responsible for learning and abstracting features from the input data. These layers allow the network to discover nonlinear relationships between the inputs and the outputs. The output layer is the last layer in a neural network, and it produces the network's output. The number of neurons in the output layer is determined by the number of classes or outputs in the problem that you are trying to solve. The number of layers and neurons in a neural network can vary depending on the problem, data, and architecture. Adding more neurons in the hidden or output layers makes the number of weights grow quickly. For instance, the neuron on the previous slide has one hidden layer with 2 neurons and an output layer with 1 neuron. The network is fed with an input of dimension 3, 2 features and a constant, 1, for the bias term. Each connection indicates a weight or parameter of the neural network. Hence, the hidden layer has 2 by 3 weights, the number of hidden neurons times the input dimension. The output layer has 1 by 3 weights, the number of output neurons times the input dimension for the output layer. The total number of weights is 2 by 3 plus 1 by 3 equals 9. Similarly, the number of weights of the neural network that is shown on this slide can be calculated as follows. Number of weights equals 4 by 3 plus 1 by 5 equals 17. Adding layers as well as neurons in each layer rapidly grows the number of weights. While more layers in the network and more neurons in a layer improve the representation power of the network, they can also increase training time and inference or prediction time. Having a network with 2 neurons in one hidden layer is still not particularly useful for most real-life ML applications. Typically, you would use more complex neural networks to approximate more complex functions that cannot be easily described by traditional methods. The trick is to design or engineer a network architecture for the current task. For a more complex binary classification problem, you could design something like the single neuron output architecture or 2 neuron output architecture that are shown on the slide. These architectures would result in more patterns being learned from the data, which will allow the model to do a better job of separating the two classes. The single neuron output architecture at the top left of the slide has 5 neurons in the hidden layer and 1 neuron in the output layer. The 2 neuron output architecture on the right side of the slide has 4 layers, of which 3 are hidden. The hidden layers have 5, 3, and 2 neurons. The output layer has 2 neurons. Note: don't count the input layer when you consider the total number of layers for a neural network. Depending on the problem to be solved, the network can go much deeper than 4 layers. This is where the deep part of deep learning comes from. More and more hidden layers make for deeper networks. Deeper networks have more flow and analysis of the information that is received from the inputs to connect to the outputs, which makes for more capable learners altogether. For example, for a 3-class classifier, you could design something like the network on the bottom left of the slide. This multi-neuron output architecture has 5 neurons in the hidden layer and 3 neurons in the output layer. Each output neuron generates the probability for each class. As you might guess, for even more complex tasks, such as high-dimensional tabular datasets, images, or text data, more complex architectures can and have been engineered. Examples include convolutional neural networks, CNNs, and recurrent neural networks, RNNs. CNNs are engineered to better learn from image-like data. RNNs are engineered to better learn from sequential data, which is particularly useful when working with text data. No matter the number of neurons, a neural network architecture has the following characteristics. It can have several hidden layers, and it has 1 input and 1 output layer. Let's continue with a review of optimization. ML models aim to take in the model features and match the model target. In reality, almost all ML models take in the model features and make model predictions that rarely match the model target exactly. Some error occurs, which is represented by the difference between the target and prediction values. The goal is to train until the error gets as small as possible. One method for optimization is the gradient descent algorithm. This uses gradients to find the minimum of a function iteratively. Steps proportional to the gradient size are taken toward the minimum, in the opposite direction of the gradient. As the gradient reduces, so do the steps between inputs, which are the weights. This avoids wasted training time. The algorithm begins with an initial point W. Update W by steps in the opposite direction of the gradient to move toward the minimum. The size of the update is controlled by the step size parameter, also known as the learning rate. If the step size is too small, the algorithm might take a long time to converge or might never reach the global minimum. The loss function, also known as the cost or objective function, plays a crucial role in the optimization process. It expresses the overall model error, and the optimization process aims to reach its minimum value. Loss functions are used in neural networks in the same way as they are used for classical machine learning linear regression models, to measure model predictions against actual labels and evaluate how well the model is performing, as well as to measure the optimization applied during the learning process. The type of loss function significantly affects the optimization or training of a neural network. The choice of the loss function relates to the task that you are trying to solve. For binary classification problems, cross-entropy for logistic is a suitable loss function. The term P is the output of the sigmoid activation function, which validates that the problem is binary classification. The loss function can be used to optimize the weights of the network by using gradient descent. For regression tasks, a metric such as mean squared error is suitable. As required, this loss function is differentiable, meaning the derivative exists at every point in its domain, and is suitable for predictions and labels that are numerical values. Now that we know about single and multilayer perceptrons, as well as the gradient descent algorithm, let's discuss how to train a neural network. Training a neural network shares some similarities with classical machine learning, such as the use of optimization techniques like gradient descent and loss functions. However, neural networks differ in their use of activation functions. To train a neural network, the predicted output is compared to the actual output, and this difference is quantified by the loss function. The goal is to minimize this loss by adjusting the network's weights and biases through gradient descent. The nonlinear nature of activation functions allows the neural network to effectively differentiate between various outcomes when applying gradient descent, enabling it to adapt to a variety of data. Activation functions analyze, judge, or activate information that comes into the neurons from the weighted inputs. If these activation functions were linear, like identity functions with no activations, for example, then everything would go through the network linearly. The network wouldn't be able to learn any nonlinear patterns. Nonlinear functions are used for activation functions. The flow of inputs through the network with nonlinear activations ensures learning of nonlinear patterns in the dataset. This would not happen with linear activations. With more neurons and more layers that are equipped with nonlinear activation functions, the whole network will be able to learn more and more complex patterns in the data. Basically, the network can learn more complex nonlinear relationships between the input, features, X, and output, label, Y. For example, as seen with the use of the sigmoid function in logistic regression, which can be thought as a neural network with only one layer and only one neuron in that layer. That one nonlinear activation function was a successful decision-making function. It successfully identified a particular pattern, a class, in that case. It answers the question, is that simple pattern there or not? The probability of the class being there was mapped between 0 and 1, where 0 meant absence of the feature, and 1 meant its presence. The same goes with much larger networks. More neurons are working together, and each is activated by a nonlinear function. Each works to identify whether the pattern is present. Together, they learn more complex patterns than they would separately. Let's look at commonly used activation functions include the sigmoid function, hyperbolic tangent function, and rectified linear unit, ReLU, function. Sigmoid function. This function is a popular activation. It's often called a squashing function because it squashes any real value input to some value in the range, 0 through 1. For this reason, in the earliest neural networks, scientists who were interested in modeling biological neurons that fired or didn't fire started using the sigmoid function as a natural choice for the activation function. When attention shifted to gradient-based learning, the sigmoid function was a winner again because it was differentiable with an easy-to-compute derivative. Sigmoid functions are still widely used as activation functions on the output units when you want to interpret the outputs as probabilities for binary classification problems. However, the sigmoid function has mostly been replaced by the simpler and more easily trainable ReLU function for use in hidden layers. Hyperbolic tangent, tanh, function. Similar to the sigmoid function, the hyperbolic tangent function also squashes its inputs but to the range, -1 through 1. Note that as the input nears 0, the hyperbolic tangent function approaches a linear transformation, as does the sigmoid function. Although the shape of the function is similar to the sigmoid function, the hyperbolic tangent function exhibits point symmetry about the origin of the coordinate system, not at 0.5, as with sigmoid. ReLU function. The rectified linear unit, ReLU function, has been the most popular choice since about 2022 because of the simplicity of implementation and its performance on a variety of predictive tasks. The function involves a simple nonlinear transformation. It retains only positive elements and discards all negative elements, and sets the corresponding activations to 0. For binary classification problems, the sigmoid function is a good choice because it outputs values in the range, 0 through 1, which can be interpreted as the probability for each class. For example, An output value of 0.89 suggests an 89% chance that the data point is class 1 and an 11% chance of being class 0. For multi-class classification problems, the softmax function, which is also known as the normalized exponential function, extends the sigmoid function to multi-class classification. The function normalizes, scales, the outputs to the range, 0 through 1, and ensures that they sum to 1. This is what dividing each exponential by the sum of all does here. For example, if you have a 3-class classification problem and 3 output neurons, softmax outputs from each neuron a value in the range, 0 through 1. One class probability is produced for each class, and the sum of the 3 probabilities will add up to 1. Out of these 3 probabilities, the highest decides the final class prediction. Note, 11 is the input weighted sum at each neuron. How many classes there are, how many neurons are needed. For regression, a good choice for an output activation function is the linear function, as seen with linear regression, or ReLU if negative values are not of interest. Data flows 2 ways during training, forward propagation and back propagation. It passes through the neural network several times, forward and then backward. Every time the full dataset passes through the network is called an epoch. In forward propagation, data flows toward the output layer from the input layer to generate a prediction. The predictions are often used to compute the loss function, which is then used for backpropagation. Backpropagation involves computing the loss function from a batch of data and using the gradients to update the weights of the network from the output layer all the way back to the input layer. Upon iterating over all the samples of a given training dataset for a forward propagation and backpropagation, the network has completed one epoch. The forward pass is called forward propagation. The data goes forward from the input layer to the output layer of the neural network. The activation functions transform the data that goes forward. Upon completion of a forward pass, the model predictions are evaluated against the true labels by using a loss function. The loss function is then used to compute the gradient with respect to the weights, which are used during backpropagation. The data moves from the output layer to the input layer in backpropagation. Based on the output of the loss function, gradient descent is computed and backpropagated. This cyclic process continuously updates the weights, optimizing the model performance. Let's walk through an example for building and training a neural network for a binary classification task. There is no bias for simplicity. Consider 2 inputs, x1 equals 0.5 and x2 equals 0.1. There is one hidden layer with 2 neurons and one output neuron in the output layer. To complete this network, all 3 neurons use a sigmoid activation function. You can choose different activation or output functions for different layers. However, all neurons in the same layer will use the same activation. The activation functions are also hyperparameters of the neural network and need to be tuned by using a validation set to identify which choices perform best. To stay organized and to make it easier to follow the computations, notice the notations in this diagram. The hidden neurons are labeled as H1 and H2, and the output neuron is labeled O. Each one has their own upper scores, in and out, to represent the incoming and outgoing values at that neuron. To pass these inputs forward through the network, you need to start with initial values for all 6 weights. This is traditionally called initializing the network. You need to start somewhere, so you guess, and if that guess isn't correct, you adjust as needed. Similar to the activation and output functions, you can choose from popular ways to initialize neural networks or create your own. The slide lists initial values for the weights, W1 through W6. Now you have what you need to push the 2 inputs through the network and compute the network's output based on those 2 inputs. The process is as follows. Move from the input layer to the hidden layer. With the inputs 0.5 and 0.1, the weighted sum arrives at the first hidden neuron, H1. The following is calculated. H1 and equals 0.15 times 0.5 plus 0.25 times 0.1 equals 0.1. This weighted sum is then transformed by the sigmoid activation function into 0.52. Similarly, with the inputs 0.5 and 0.1, the weighted sum arrives at the second hidden neuron, H2. The following values are calculated. H2 in equals 0.13, and H2 out equals 0.53. These output values from the first layer, 0.52 and 0.53, will be the inputs to the next layer's neuron. One more pass forward through the neural network is needed. Imagine how, in deeper networks, this might mean that training goes for much longer. First, to compute the weighted sum that is arriving at the output neuron, use the inputs that are coming from the hidden neurons. O(n) equals 0.5, 2 times 0.4, plus 0.5, 3 times 0.45 equals 0.44. The weighted sum is then transformed by the sigmoid activation function to 0.61. This is the final output of the neural network. By using a decision boundary at 0.5 for binary classification, this would be classified as class 1, because 0.61 greater than 0.5. If the true class of the x1, x2 equals 0.5, 0.1, inputs is 1, you would be lucky because you build a good network on the first try. However, most of the time, the first model, neural network, that you build won't be right. If the output didn't match the target, given this neural network architecture, all 6 of the weights would need to change such that the error between the output and target gets smaller. You can use gradient descent to move the model in the opposite direction of the error's gradient, one step at a time, to minimize the model's error. But how do you compute this error function so that you can then adjust the model, weights, accordingly? Now that the model has completed forward propagation and generated a prediction, you need to evaluate the predictions. The loss function evaluates the model predictions, O, against the true labels, Y. Because this example describes a binary classification problem, a suitable loss function is cross-entropy loss. By using the predictions, the loss function computes the loss to be minus 0.494. The backpropagation process is quite complex, even for a simple example like this. It involves applying gradient descent over the derivative of chain activation functions related to each weight. For the example with sigmoid, skipping detailed derivations leads to the following equations. Then, calculating for only the sample used in this example, we have the following by substituting the example values. Finally, applying the update rule leads to the new value for weight W5. Considering the step size of 0.01, we can calculate the new weight. This process is followed to update all weights for each backpropagation. Let's put everything together. The forward pass propagates the input data through the network layers by applying the activation functions until reaching the output layer. The loss function then measures the error between the predicted outputs and the true labels. Backpropagation uses this error to update the weights via gradient descent, adjusting their values to minimize the loss. This process repeats for multiple epochs, passing the dataset through the network multiple times to optimize the model predictions. Training concludes when the model achieves the desired performance agreed upon by the data science and business teams. By iteratively updating the weights based on the prediction errors, the neural network gradually learns to make more accurate predictions on the training data. In the next lesson, we will explore some neural network examples. Thank you for watching.